Before I share how I found a new way of approximating pi, I want to tell you how I reached it. Completely unknowingly, I just followed a spark of curiosity that wouldn't let me sleep. It was late at night, and a strange question appeared in my mind. How can the number 5 be related to any n squared? It sounded random, but it felt meaningful. So I started dividing n squared by 5, from 1 squared to 20 squared, just to see what patterns might appear. Then I thought, let me remove the decimals completely. I'll take discrete values using floor and ceiling and call the leftover the residual. Positive for the floor, negative for the ceiling. And right there, patterns began to form. I wondered if this only happened with 5. So I tried the same process for 2, 3, 6, 7, and the same structure fit perfectly. That's when I decided to give names. Floor became the lower layer, and ceiling became the upper layer. Inside these upper and lower layer sequences, I noticed smaller repeating steps, patterns of change. I called them delta U and delta L. These tiny fluctuations were like the heartbeat of each layer. When I looked them up in the OEIS, some of these delta patterns already existed in other contexts. But one of them immediately reminded me of something classical, the Wallace product for pi. For mu equals 2, the ratio delta L over delta U gave results identical to the Wallace product, the same infinite product that converges to pi. But unlike the historical Wallace formula, mine came purely from discrete floor and ceiling functions. No calculus, no integrals, just integer structure. Naturally, I wondered, what about other mu? So I wrote a C program and calculated it. First for mu equals 2 up to 200, then for random values of mu all the way to 100,000. The pattern was shockingly consistent. From all those computations, I realized a clear law. 75% of positive integers, all those not divisible by 4, make the DSRS product converge to pi. The remaining 25%, the multiples of 4 converge to 1. To be sure, I shared it on StackExchange and got a formal proof sketch confirming this behavior. That gave mathematical backing to what started as a simple curiosity test in code. But something else caught my eye. The lower and upper sequences themselves always increase, but their deltas start to behave differently as mu grows. For small mu, they rise and fall like clean waves, almost periodic. But for larger mu, those waves begin to distort, drift, and lose rhythm. It felt like watching order dissolve, an arithmetic form of entropy increasing with mu. This journey began with a late-night question about 5 and squares. Following that spark led me to discrete square residual structures, a framework where most integers yield pi, others yield 1. If this story inspired you, read the preprint linked below and subscribe for more of my math explorations.